right? So we basically know what happens when magnetic field or when charge moves in a magnetic field. Now suppose electric field and magnetic field are both present. One of you tell me, when a charge Q is in an electric field E, how much force does it experience due to the electric field?
Q into E.
Okay. The electric force, or maybe I should say electrostatic force that it experiences is QE. It's a vector equation. Along with direction, you can tell it will be QE. Okay. And we know that the magnetic force that it experiences is Q V cross B. So if a charge is moving in the presence of both electric and magnetic fields simultaneously, the net force acting on the charge would be the sum of these two forces, that is QE, electrostatic force, plus QV cross B, the magnetic force that acts on it. Together you can write it as Q E plus V cross B. Do any of you know the name of this force?
Lorentz force.
It's called Lorentz force, okay, named after a scientist. Basically, the net force experienced by a charge due to both electric and magnetic fields, we call it as Lorentz force. Okay. Seshank, you didn't miss anything. We just started the class. When a charge moves in a combination of electric as well as magnetic field, what happens is what we were discussing. Okay. So you can be asked simple direct questions based on this. They can give you the charge, velocity with which it is moving, electric field, magnetic field, and ask you what is the net force acting on it. Simple questions possible. Now see, it's like there are two forces acting on the charge. When there is an electric field and also a magnetic field, electrostatic force will act, magnetic force will also act on the charge. So it's like two forces are acting on it. Now, it's not necessary that these two forces are in the same direction always. Fine. And it's also possible that sometimes these two are opposite to each other. And it's also possible that they cancel each other. Okay, we'll discuss that case. Special case actually. Charge moving in electric as well as magnetic field such that the net force on it is 0. Let's see how that can happen. Now we know the net force acting on it is QE, that's the electrostatic force, plus Q V cross B. We want this to be 0. Okay. Q gets cancelled. That means electric field should be negative of V cross B. Okay. If that happens, magnitude wise and direction wise, if this equation is satisfied, then the net force on the charge would become 0. Okay. Now we know V cross B will be perpendicular to V as well as B, both of them. Okay, cross product of two vectors is perpendicular to both the vectors, right? So V cross B, since it is perpendicular to V and B, and for the net force to be 0, electric field should be in the negative of this direction. It means electric field must be perpendicular to both velocity and magnetic field. Fine. And magnitude is also important. V cross B, the magnitude is VB sine theta. It means the magnitude of electric field should be equal to VB sine theta. Direction should be exactly opposite to V cross B, then the net force on the charge becomes 0. Okay. Now one of you tell me, generally, if net force on a charge is 0, what happens to it? If net force on any object is 0, what happens to it?
Sir, if it has a velocity, it will continue with that velocity. If it has rest, it will be at rest.
So basically, nothing will happen to the object. If net force is 0, it will continue doing what it is doing. Newton's first law, law of inertia. If it's at rest, it will continue to be at rest. If it's moving with some velocity, it will continue to move with the same velocity. Correct. Okay, so just remember this case. It is possible that when both electric and magnetic fields are acting, the net force on a charge becomes 0. Okay, you just need to write an equation balancing the electrostatic force and the magnetic force. From that, you can tell how much field is necessary, or they can ask you any question based on this. They may give you velocity, magnetic field, ask you the electric field, or they may give you electric field and velocity, ask you the magnetic field. So you will be able to answer based on that. Okay, let's try one question like this. Charge doesn't matter anyway. Let's say a charge Q is moving, let's say with a velocity, how much? Let's assume some 10 I cap. 10 is actually very less, but let's take 10 I cap meters per second. In a magnetic field, let's say 2 J cap Tesla. Derive how much electric field should be applied such that net force on the charge is 0. Okay, type your answers in chat. Okay, Yash and Shashank, your answers are correct. Others also calculate quickly. Okay, so see, the electrostatic force should cancel out the magnetic force. So QE should be negative of QV cross B. Q you remove. E should be negative of V cross B. That's all. So electric field is negative of V is 10 I cap cross B is 2 J cap. 10 to 20, I cross J is K. So this becomes minus 20 K cap Newton per Coulomb. Okay, since velocity and magnetic field were in SI units, the electric field will also be in SI units. Okay. Now, there is a device which makes use of this property, okay, which makes use of the fact that electric force can cancel magnetic force, okay, and it is used to select particles moving with particular velocity, and the name itself suggests what it does. It's called a velocity selector. So what it does is, from a stream of charged particles, okay, it will filter out those particles moving with a particular velocity. Means it will allow only those particles to pass which move with a particular velocity. Others will be removed. Okay. Now, how does it work? First, now see, we know that for the net force to become zero, E should be negative of V cross B. That means electric field must be perpendicular to both velocity and magnetic field. So electric field has to be perpendicular to magnetic field for net force to be zero. Generally, when electric field is perpendicular to magnetic field, we call them crossed fields. Okay, whenever electric field is perpendicular to magnetic field, we call them as crossed fields. So imagine something like that. Let's say there is a magnetic field directed into the screen like this. Uniform magnetic field we'll take. Okay. Imagine a charged particle entering into this region. Assume it's a positive charge. And it enters to the right like this with a speed v, or with a velocity v, you can say. If v is to the right, magnetic field is into the plane. One of you quickly tell me, what is the direction of the magnetic force on it? Or what is the direction of v cross b? Direction of v cross b.
Upwards, sir.
Okay, v cross b, it will be in the positive y direction. Okay, that means the magnetic force would be acting upward. So you can say v cross b is this way. Then for the net force to become zero, we know that electric field should be exactly opposite to it. That means the electric field should be in this direction. So along with this magnetic field, you need an electric field which is directed downwards. Everywhere it must be present. Okay, the green arrow is the electric field. So v cross b is upward, electric field is opposite to it. In this case, we assumed magnetic field into the screen, that is, it's in the z direction. Velocity is in the y direction. Downward means negative y. They are perpendicular to each other. Sorry, not velocity. What am I saying? Electric field is in the negative y direction. Okay, the green arrows represent electric field. So electric field y direction, magnetic field z direction, they are perpendicular. That's why they're called crossed fields. Now when a charged particle enters this way, what will happen? The moment it comes inside, visualize the charged particle somewhere here. There will be a magnetic force acting on it. V cross B is upward, and we took the charge to be positive. So Q V cross B will be upward. And electrostatic force QE will be downward, because if charge is positive, the electrostatic force is in the same direction as the electric field. So QE, electrostatic force, will be downwards. So QV cross B upwards and QE downwards. They balance. Okay. Of course, for them to balance, you need a particular magnitude of electric field. What should it be? The magnitude of electric field should be equal to magnitude of V cross B. That is compulsory. Then only these two forces will balance. So there's a particular amount of electric field that you need to apply. Or you can tell in the reverse also. Suppose electric field is fixed and magnetic field is fixed. There is a particular velocity for which the net force becomes zero. Not all velocities are going to have net force zero. Only particular velocity will have net force zero. That is what this device makes use of. Okay. The magnetic field is preset, already fixed. Electric field is also already fixed. Then if electric field and magnetic field are fixed, only those charges will experience zero force which move with this particular velocity, which satisfies this equation. That is why it's called a velocity selector. Only those particles moving with that particular velocity can pass without experiencing any force. Okay. Now, what if this was a negative charge? Suppose a negatively charged particle enters. Then imagine the negative charge somewhere here. V cross B is upwards. Q is negative, means QV cross B will be downward on it. On the negative charge, QV cross B will be downward. Then the other force, electrostatic force, QE. Q is negative, then electrostatic force on negative charges will be opposite to the electric field. This time, electric field will be in the upward direction. Not electric field, sorry, electrostatic force will be in the upward direction, QE. You don't have to reverse the field direction. Force will automatically be in the opposite direction and those two will balance. So it doesn't matter in a velocity selector, it doesn't matter whether the charge is positive or negative. Okay, so the device will be like this. It's somewhat like a box. Charged particles enter into it from one side, and on the other side there is an opening. What will come out from that opening? Only those charges which did not deviate will come out from that opening. Okay, and when will charges not deviate? When they move with this particular velocity which satisfies this equation. Only those charges will not deviate. Okay, so that is why this device is called a velocity selector. It allows only charges of a particular velocity to pass through it. Other velocities will get deviated. They won't come out from the other end. Okay. So is the idea clear to all of you how a velocity selector works? One of you quickly tell me, why does it need crossed fields? Why does a velocity selector need crossed fields? Why should electric field be perpendicular to magnetic field?
So when they both are perpendicular, the forces will cancel out.
Only when electric field is perpendicular to magnetic field, there is a chance of the net force becoming zero. Okay, so it is compulsory that the electric field has to be perpendicular to magnetic field. Now there's one more condition also. Here, listen. We assumed velocity of one charge is in the x direction. That is how we got V cross B upwards. That is how we said electric field should be downwards. Now when velocity of the charge is in the x direction, then V cross B was in the y direction. Electric field we took in the negative y direction. If another charge enters with another velocity, some other direction of velocity, then these two, then the magnetic force and electric force won't cancel. Why? Because if the charge enters like this, the magnetic force acting will be this way. Electric force acting will be this way, or maybe this way. They won't cancel. So it's compulsory that all the entering charges enter with the same direction of velocity. They can enter with different magnitudes of velocity, but direction with which the charges are sent into this instrument should be the same. Okay. So in a velocity selector, I'm just calling it as VS, electric field is perpendicular to magnetic field. We know that. And the velocity must be perpendicular to both of them. So effectively, it's like all three should be mutually perpendicular. If one is in the x direction, one should be in the y direction, and the third should be in the z direction. Like in this diagram, magnetic field is in the z direction, electric field is in the y direction, velocity is in the x direction. All three should be mutually perpendicular. Only then a velocity selector works properly. Okay. So if velocity is perpendicular to magnetic field, V cross B will simply be VB. Okay, sine 90 degree becomes 1. So V cross B is simply VB. Therefore, the electric field needed is simply VB. That means the velocity needed is electric field divided by the magnetic field. Only charges moving with this velocity will come out from the other side of the instrument. The remaining charges will get deviated. Which way will they get deviated? Listen, there are two forces acting on the charge. One is QV cross B, the other is QE. Suppose velocity is more than E by B. Okay. If the speed of the charge, okay, velocity, direction is fixed anyway. So you can talk in terms of speed. If speed is more than E by B, magnetic force dominates. Because magnetic force is QV cross B. No, if you give high speed, that force will become too much. And it will deviate in the direction of magnetic force. Okay. If speed is less than E by B in a velocity selector, then which force will dominate? Electrostatic force will dominate. Then the charge will deviate in the direction of electrostatic force. It won't go straight. The only speed with which going straight is possible is this, when all three are mutually perpendicular. Okay. So charges moving with that speed will come out from the other side. Remaining charges will get deviated either upward or downward, sideways, whatever it is. They won't go straight. Is the idea clear to all of you, velocity selector? If you have any doubts, you can ask. Okay. So how do they ask you questions based on velocity selector? Same, like they may give you velocity and magnetic field, ask you electric field, or they may give you electric field, magnetic field, ask you with what velocity the charge should move such that it doesn't experience any force or it passes through the selector. Such questions. Fine. Next thing we need to discuss is the magnetic force acting on a current carrying wire. One of you quickly tell me, what is current? What is electric current? What is electric current? Basically, flowing charge is what you call as current. Okay, flowing charge is nothing but moving charge. Now, if there's a current wire placed in a magnetic field, let's say magnetic field in this case is inwards, and you place a current carrying wire in it. Like in your syllabus, you only have current arising from the flow of electrons. Okay, in solid conductors, it is the conduction electrons that result in a current. So let's say current is flowing this way. Now tell me, generally, not related to this case, what is the net charge of a current wire, current carrying wire in any circuit? Like suppose there is a simple circuit like this with a resistor and a cell. We know current flows in it, current flows this way. So if I take, say, this part of the circuit or this wire, what is the net charge in that wire? Positive, negative, zero.
Zero, sir.
Yes, how do you say it is zero?
Sir, here like the electrons will be flowing in it, right? So inward, inflow is equals to outflow. So we'll have net charge zero.
Inflow of what is equal to outflow of what?
Like here, the conduction electrons will keep
Ah,
on circulating, right?
oh, see, electrons are flowing in, electrons are flowing out. That's okay. Are there protons or not? That is my question.
Yes, they are there, but they are not moving it.
They are not moving, that's all. And the number of electrons, number of protons, is it same or not?
Yes, sir.
It is same. Okay. See, generally circuits are made of neutral materials only. Fine. Like in this wire, if we say a current is flowing this way, imagine what happens. In the wire, there will be positive charges. The green dots are the positive charges. By convention, the direction of current is the direction of flow of positive charge. But in solid conductors, positive charges don't flow. It is the electrons that flow, and we know that. So the protons are at rest inside the nucleus. They don't move. Electrons will be moving. If current is going up, it means electrons are going down like this in that wire. And there will be a lot of them. A lot of conduction electrons will be flowing in a conductor. Positive charges don't move, negative charges move. But if you take some part of this wire, say from here to here, the net charge in that part is going to be zero itself. Okay, so remember this idea, all of you. In current carrying wires, the net charge is zero. Both positive charge, negative charge is there. Some negative charge is flowing, that's all. Okay, fine. Now this wire, if it is placed in a magnetic field, there are moving charges inside the wire, and moving charges experience a force due to magnetic field. So this wire is going to experience a force due to the magnetic field. Now let's consider one small part of this wire, say from here to here. The net charge on that part is also zero, but in that element, negative charge is flowing down. Okay, so electron is flowing in the downward direction. So electron's velocity is this way. Magnetic field is into the plane. So if you do V cross B, it will be in this direction. This is the direction of V cross B. And we are taking electron. Electron is a negative charge. We are considering the force on an electron. Electron is negative charge. So minus V cross B will be in this direction. Okay, so Q into V cross B is in this direction. It means that that small part of the wire will experience a force that way. Okay, small amount of force, because it'll have only a small amount of moving charge in it. Net charge is zero. I won't say it has a small amount of net charge. Net charge is zero, but the moving charge in that small part of the wire will be a few electrons. So that's a small amount of charge. So effectively what will happen? It experiences a small amount of force in this direction, dF. And not just that element, every element of the wire will experience a force. Okay, since it's a small force, I'll just indicate with a small arrow. So on every element of the wire, there will be force acting like this. And as a result, if all these vectors don't cancel, the wire itself could experience a net force. Okay, so that is the effect that a magnetic field has on a current carrying wire. It can exert force on the wire. Whether that force cancels out and becomes zero or not depends on the shape of the wire. Like in this case, if you consider only this much wire, these orange vectors, they are not going to cancel definitely. They will produce a resultant. Okay, fine. So consider a wire carrying a current I. Okay, I got one question. Can it depend? I think you are referring to the force. Can the force depend on the strength of the magnetic field also? Definitely. Okay. F is equal to QV cross B. It depends on how strong the magnetic field is. And this force on the wire arises from that itself. So it will also depend on the magnetic field. Yeah. But see, we are now talking about force acting on a current carrying wire. So it will be better if we write the formula F is equal to QV cross B in terms of the current instead of the charge. So we are going to change that formula into current terms. Let's say there's a current carrying wire like this. Assume the current is I. Okay. Now consider a small part of this wire, say from here to here. Charges will be flowing. See, it's actually electrons flowing down, flowing in the opposite direction of current. You can assume protons are flowing this way. They produce the same effect. So let's assume positive charge is flowing in the direction of current. Now, by definition, we know I is dq by dt. So the charge dq becomes I dt. What charge is this? The charge that would flow through any cross section in a time dt. Okay. Assume this distance, the length of this element from here to here is dl. Since it's a small element whose length tends to 0, this actually has to be a straight line, straight arrow. I'll draw it straight itself. Okay. Just for us to be able to visualize, I have taken significant length. It should actually be tending to 0. So we are considering a very small part of the wire. Let its length be dl. And let's consider a vector dl bar in the direction of current. Through that element. Now in time dt, some charge dq is going to pass through that element, through that part of the wire. Can one of you tell me with what speed electrons move in a conductor? What is the name given to that speed? When current flows in a conductor, what is the speed of electrons called?
Drift velocity.
Drift speed or drift velocity. Correct. Let it be v. Okay. So a charge dq will be passing through this element with a speed v. Okay. In time dt. Now let's say there exists a magnetic field B. It doesn't matter which way the magnetic field is. Assume the magnetic field is B. Into the screen, rightward, leftward, downward, whatever it is, there is a magnetic field B. Then the force acting on that element would be a small force dF is equal to the charge that moves in that element dq multiplied with v cross b. Okay, where v is drift velocity. And simply by definition, velocity is displacement divided by time. So you can write it as dl by dt. So what does the expression change to? dq into dl vector cross b vector divided by time dt. Time is a scalar quantity, doesn't matter where you divide it. And dq by dt becomes current. Therefore, df, the force acting on the element of the wire, becomes I dl cross b. Okay, very, very useful equation. This is the force acting on a current element due to the magnetic field. Is this clear to all of you? Any doubt in this? How we got the expression for the force on the element? Okay. Now, since it's a small element, the force acting on it also will be small df, but such small forces will be acting on every element of the wire in a direction perpendicular to the length of that element. Direction is most important. You see what we got here, dl cross b means this force df is perpendicular to both the element and the magnetic field. Okay, the force acts perpendicular to the current element. It acts perpendicular to the wire at that point. This is very important because force is a vector quantity, direction you need to know. Okay, now we got force on one element of the wire, but usually that will be tending to 0 because in a small element of the wire, the charge is small. QV cross B also will be very small. The moving charge is small. Okay, so DF usually will be tending to 0. We will not be interested in it. One of you tell me how to calculate total force on the wire. Yash, don't answer. Anyone else? We know force on one element of the wire. How to calculate total magnetic force on the entire wire? Eh? Generally, if you know what happens to one element, how do you tell what happens to the entire system? Manas, any answer?
Sir, I will send you a text message, sir.
Okay, fine. Shashank,
So we have to integrate.
what did you say?
We have to integrate.
You have to integrate, correct? You need the combined, you need the combined effect of forces acting on all elements. So integrate all the forces. Fine. But okay, we know df is IDL cross B. So it becomes integral I dl cross B. Again, another very important equation. This is how you can calculate the total force on the wire. Now tell me, will every part of the wire be carrying the same current or not? If it's just one wire with no junctions in between, will every part of the wire have the same current or not? Anyone?
Sir, it will have the same amount.
It will have the same current, okay? Because in your syllabus, we only deal with such cases. It's called a steady current, okay? Or steady state flow of charges. Current should be same everywhere in one branch, okay? So I can be kept out of this integral because in every element, the current is the same. Therefore, force can be expressed as I integral dl cross B. Okay. This is the general equation. Now we can derive one specific equation from this. Okay. If magnetic field is uniform, okay, we are imposing one condition. So the result that we get from this will be valid only when the condition is satisfied. So if magnetic field is uniform, then the force can be written this way: F is equal to I integral dl cross B. The magnetic field can be kept outside the integral. Anything which is constant can be kept outside an integral. But here you can't write B on the left side because A cross B is not the same as B cross A. They are exactly opposite to each other. So we are not supposed to change the order in a cross product. That is why we write F is equal to integral DI integral DL cross B. One of you tell me, what was DL? In the derivation, what did we call as DL?
Small part of the wire.
DL was the length vector of a small part of the wire. Correct. Now we need to integrate all those small length vectors. So let's just visualize the DL here. For that element, the DL vector is like this. For the next element, the DL vector would be like this, and so on. So integrating DL means taking the resultant of all these vectors. Okay, all the way from the starting point of the wire to the ending point of the wire. Like whichever part of the wire you want the force on, you have to integrate all the lengths. Can one of you tell me how to visualize the resultant of the summation of a number of vectors like this? Like if there are two vectors, suppose they are joined one tail to one head, we use the triangle law of vector addition. This will give us the resultant. How to add so many vectors and get the resultant direction?
So do we reimagine this wire as an as a straight wire of effective length.
Imagine this wire as a straight wire.
Of effective length.
How much is that effective length? From where to where should we take the effective length? Should we keep the length same and stretch the wire straight? Or from which point to which point should the length be? That is my question.
I'm not sure.
Okay. See, remember, we are not just integrating the magnitude of DL. Fine. If you had integrated the magnitudes of DLs, you would have gotten this curved length. But that is not what we are doing in this integral. It is clearly an integral of the vector DL. Okay. So you have to sum up a number of DL vectors, and multiple vectors can be added using the polygon law of vector addition. Basically, it's a repetitive application of triangle law. For example, suppose there are 3 vectors, one like this, 2, 3. You can take a 4th one also if you want, any number. We want to visualize their resultant. First, if you add A and B, their resultant will be like this. What you are looking for is A plus B plus C plus D. But use the triangle law, you can add A and B and get the resultant like this. Now this is A plus B, which is one vector now. Next, add C to it. You will get this vector. This is A plus B plus C. Now you add D to it. Effectively, it becomes a vector drawn from here to here. That is the sum of all 4 vectors. This is what we call as polygon law of vector addition. You don't need these middle vectors. Whichever series of vectors you need to add, place them one by one. Okay, one next to the other in order. What do we mean by order? Second tail at the head of the first, third tail at the head of the second, fourth tail at the head of the third, and so on. They are all in order. If you arrange a set of vectors in order, the closing side of the polygon taken in reverse order gives their resultant. So this vector is the resultant. We use the same idea here also. There are a lot of DL vectors, but they are all placed in order, okay, which is an advantage for us. And we want the resultant of all these DLs. Effectively, it will be the vector drawn from the starting point of the wire to the ending point of the wire. You just have to connect the first tail to the last head. That will be the resultant. Okay. So this vector is what we call as the L vector. Integral DL will become L. And how do you draw the L vector? You have to take an arrow, or you have to take a vector from the starting point of the wire to the final point of the wire. Whichever part of the wire you want to calculate the force on, that becomes the L vector. So remember, this point is where most students make a mistake. They take the curved length for L. That is not correct. You have to take the shortest distance between the first point of the wire and the last point of the wire. So in case of uniform magnetic field, the formula changes to I L vector cross B vector. But remember, condition is most important. This has very limited application. Field has to be uniform, only you can use this. Only then you can use this. Don't blindly use IL cross B always. The correct formula is integral IDL cross B. Only when field is uniform, it changes to this form. Okay. I hope the derivation is clear to all of you. We use F is equal to QV cross B to derive DF equal to IDL cross B. That gives us the force on one element of the wire. If you want total force on the entire wire, then you'll have to integrate the forces on all the elements. You'll have to integrate DFs, and this is what it changes to. Generally, it is integral IDL cross B. In a specific case where magnetic field is uniform, it changes to IL cross B. So this is specific when field is uniform. Okay. Let's try questions based on this. Okay, let's take a curved wire. Assume there's a wire in this shape. The radius of curvature of this part is given to you. Let's say it is R. And a current I is flowing through it. And there's a magnetic field directed out of the screen. Uniform magnetic field itself. Assume its magnitude is B bar. It is directed out of the field. Calculate force acting on this part of the wire AB. Magnetic force on AB. And give your answer as a vector. Do this, all of you. Magnetic field is uniform. So the formula becomes, you can use the formula directly. I L vector cross B vector. Just think of what to substitute. The radius of that curved part is R. What happened? Why is it taking so long? We only need the force on the part AB. Okay, Isha, can you unmute?
Yes, sir.
Any answer? See, we know the current is I. Magnetic field is B, that is given to you. All you need to know is the L vector. and then take cross product with B vector. From where to where should the L vector be drawn? Okay, anyone else? L vector should be taken from where to where?
Sir, in the direction of current from A to B.
In the direction of current from one end of the wire to the other end, like of the part on which you want the force. Like in this derivation also, we took L vector from this point to this point. Basically, in the direction of current, you have to take the vector. Okay. So here it will be the vector drawn from A to B like this. So in this problem, this will be the L vector. Can one of you tell me that vector in terms of I cap, J cap? Because we need to take a cross product here. How to write it in terms of I cap, J cap? How much is its X component? Like from here to here, how much is this?
RI cap.
R. How much is its Y component? That is also R itself, R J cap. Then the vector L will be Ri cap plus Rj cap. Because R is the radius of that curve. Okay. Magnetic field is B out of the screen. Out of the screen is K cap. That's all. Current is I. Now all you need to do is take that cross product. L vector is Ri cap plus Rj cap. Cross magnetic field is B K cap. This I is current. Don't confuse it with I cap. Okay. So I current multiplied with first Ri cap cross B K cap. RB will get multiplied. Okay. What is I cross K?
Minus
Minus J. So minus RB J cap. Next, RJ cap cross BK cap. Again, RB will get multiplied. What is J cross K?
I.
J cross K is I. Okay. So I, J, K, J cross K is I only, no? Fine. Right. So this becomes plus RB I cap. So what is the answer? IRB multiplied with minus, no, I cap minus J cap. That is the force acting on that curved part of the wire. We can visualize it in the diagram also. You can see the length vector. Okay, it's at a 45-degree angle. Magnetic field is out of your screen. So place your right hand fingers along that length vector and curl them out of your screen. The thumb will point this way. So it has, the force effectively has a positive X component and a negative Y component. That is what we got here. You can visualize it element by element also. Forget the length vector and all. Take a small element of this wire, say from here to here. Current is flowing like this. So IDL is in that direction. B is out of your screen. Then IDL cross B, the force DF will be this way. On every element, there will be a force acting inwards like this. On every part of the wire, there will be a force acting inwards like this. And these are all of the same strength. Then the resultant is going to be in this direction. That is the total force on that arc. Is this clear to all of you? You have to visualize it like this also. If any of you have any doubts, you can ask. Okay, fine. Next, what will be the magnetic force on a current carrying loop in a uniform magnetic field? Like what I mean is, suppose the wire is a closed wire like this. Let's say a current I is flowing in it. You may ask, how can a current simply flow in a wire like that? Assume there's a small cell somewhere. Effectively, it's like this. Okay. So tell me, from where to where will you take the L vector? In this case, the magnetic field is uniform. So the force we are going to use, force formula we are going to use is I L cross B itself. But from where to where should the L vector be taken? I want force on this entire loop. So from where to where will you take the L vector? Okay.
So can we like consider a point
Okay.
anywhere on the loop?
Okay, let's take one point on the loop. Call this as A. Where will you take the other point?
Like either move clockwise or anti-clockwise, you'll end up meeting at the same point.
Okay. See, coming back to the same point is correct. You can't say move clockwise or anti-clockwise. You have to go in the direction of current. Okay. DL vector has to be in the direction of current. The final L vector also has to be in the direction of current. It's not your choice which way you move. But here, if you see, what is it is correct only. If you add all the DL vectors, okay, moving this way, I'm not going to draw all of them, but you imagine adding all these vectors. The first tail is here and the last head would be here. They are at the same point. The resultant of all these vectors becomes 0. So in this case, for a closed loop, L vector is 0. And if L vector is 0, the magnetic force, the total magnetic force on a closed loop in a uniform magnetic field becomes 0. Field must be uniform. Okay. You can even visualize it like this. Consider this loop. Current I is flowing. Assume magnetic field is into the screen. Now consider a small part of this wire, say from here to here. The length vector will be this way. Magnetic field is inwards. Then IDL cross B will be kind of in the upward direction like this, perpendicular to that element, upward. On every element, there will be forces acting like that, in a direction perpendicular to the wire at that point. Okay, just imagine forces like this acting everywhere. Since there are forces in all directions and they are all of the same strength, their resultant becomes 0. That way also you can tell that the net force acting on a closed loop of current in a uniform magnetic field will be 0. And one of you tell me, what does a closed loop of current behave as?
Dipoles.
Correct. A closed loop of current behaves, all answers only Yash is giving, others also you need to stay in touch with the topic. Closed loop of current behaves as a magnetic dipole. Okay. And we just saw that the net force on it is 0 in a uniform magnetic field. This has a resemblance with electric dipole in an electric field. Okay. See, magnetic dipole in magnetic field, uniform magnetic field, we are seeing net force is 0. And we already studied, suppose there's an electric field this way, uniform electric field, and you place a dipole in it. Dipole has equal and opposite charges. Irrespective of orientation, you place a dipole in it. Doesn't matter how you place. Let's say this is the negative charge. The other one is the positive charge. Electric field exerts force on the positive charge in the direction of the field, and it exerts force on the negative charge opposite to the field. Both will be QE and QE in magnitude, but their directions are exactly opposite. So the net force on dipole in uniform electric field is 0. And from what we just discussed, we see that net force on a magnetic dipole in uniform magnetic field is 0. Okay, so electric dipoles, magnetic dipoles, they are analogous to each other. Whatever happens to electric dipole in electric field, same will happen to magnetic dipole in magnetic field. Means the same will happen to current carrying loops in magnetic fields. Okay, this is a useful property which we are going to make use in the working of a galvanometer. Okay, you'll understand later. Fine. So let's quickly go through what we discussed today. The first thing we talked about was how the net force on a charge. Okay, we discussed what happens if electric and magnetic fields are both present. The charge experiences both forces. You have to add them as vectors to get the net force. Now it's possible that the electric force cancels the magnetic force. We discussed the condition for that. For that to happen, E should be negative of V cross B. Okay, means electric field should be perpendicular to magnetic field, and magnitude also has a condition. It should be equal to VB sin theta. Okay, if these are satisfied, then the charge will experience 0 net force. Okay. Then we discussed one instrument which makes use of that property. It's called a velocity selector. Remember, in a velocity selector, electric field, magnetic field should anyway be perpendicular because net force has to become 0. Velocity should also be perpendicular. Okay, so all three must be mutually perpendicular. Then what happens? Only those charges moving with a velocity of E by B will pass through. How did we get this? From this, E should be negative of V cross B, right? And we know velocity is perpendicular to magnetic field. So the magnitude of electric field, which I'll just write as E, should be VB, or the speed with which the charge moves should be E by B. Only those charges will pass without deviation. If any charge has velocity more than this, magnetic force on it will dominate. If any charge has velocity less than this, electric force will dominate, and it will go away from that path. It won't travel in a straight line. Next, we discussed about force, magnetic force acting on a current wire. We know that current wire has moving charges. Moving charges experience magnetic force, so the wire experiences magnetic force. So from QV cross B, we derived IDL cross B. That's the force on one element of the wire. If you want total force, you integrate that. If field is uniform, it becomes IL cross B. Remember how to take the L vector. In the direction of current, you have to draw a vector from the first point of the wire to the last point of the wire on which you want the force. Then we saw one application of that. Fine. So next class, which will be tomorrow, we will discuss some more cases like this, where magnetic field is uniform and you'll have to find out the force acting on a wire. We'll also discuss cases where field is non-uniform and you find out the force acting on a wire. We'll also discuss force between two wires, parallel wires, perpendicular wires.